In this chapter, we are going to discuss dynamics, which is the forces involved, and we are going to discuss Newton's three laws of motion, and thereafter discuss about the free body diagramming and how we work on dynamics problems. So we'll define force, we'll talk about Newton's first law of motion, we'll talk about mass and weight difference, we'll talk about Newton's second law, third law, and force of gravity, and free body diagramming, and also solve problems with Newton's laws using free body diagram concept. So when we begin to explain forces, we basically want to understand what branch of physics are we studying now. Up until now, you've been talking about kinematics, and you talked about one-dimensional motion, and you learned about two-dimensional motion, which comes under the branch of kinematics. But when forces are involved, we call that part of the physics as dynamics, and the entire physics 1 is treated as mechanics, because we are talking about forces, rotational motion, forces involved in rotational motion, circular motion, linear motion, and this entire branch or entire study of physics 1 is called mechanics. So when we go ahead and talk about dynamics, which is the study of forces that causes objects and systems to move, and to understand this, we need a working definition of force. So force, in a general layman's definition, is defined as a push or pull, and something that can move an object from rest or stop an object which is already in motion. So a change of velocity is caused by this force. Whenever there is a change of velocity, we know that acceleration is involved. So the magnitude of force is used, is measured with the help of a spring scale. So you may have seen these devices in your high school. It's a scale that is graduated directly in terms of newtons. We will come to that part when we'll define what is the unit of force. But first, let's get the conceptual thing done. So we know that a push or pull has both magnitude and direction. So for example, this girl is pushing the cart. The direction of the force, we will use the symbol F for force, and it has both magnitude. So how strongly she is applying the force is the magnitude of the force, and which direction it's going is defines its path. So it has both magnitude and direction, hence force is a vector quantity, just like velocity is. And this can be force can be varied. And for example, if there's a cannon which exerts a strong force on cannonball that is launched in the air, all right, so unless and until you exert force, the ball will not be launched, which then goes off in the air. And but you had to apply force first. And again, Earth, in contrast, now there are some examples where you don't need to have a contact. For example, Earth exerts a very small force on an object which is very light. For example, a fly. Even a fly is getting attracted or has a gravitational pull towards the Earth. So our daily experiences also gives us a good idea of how multiple forces act. So if there was another person acting on this cart in the opposite direction, now which direction it would move will depend on how much magnitude of the force is applied by this person versus this person. So then the net force, we also talk about the net force, will be dependent on the sum of all the forces that are acting on it. So whether it will accelerate or not accelerate, stationary, that is something to be seen. So there are two different types of forces that we'll talk. One is contact forces that arise directly from physical contact, just like the example of a cannonball. If the cannonball is inside the cannon, and unless and until you trigger it, it's not going to go out. So this is a contact force. And then there is an action at a distance which does not depend on contact. For example, gravity, a ball getting attracted to Earth is attracted by the Earth's gravitational pull, but there are other non-contact forces, which is charges. The positive charge will get attracted to the negative charge, so there's a force of attraction between the two. And also magnetic poles, so north and south, even if they are not physically in contact, will get attracted or repelled depending on we have same poles or opposite poles. So these are action at a distance forces that do not need direct touching. Normally we'll represent forces, because the force is a vector quantity, we'll represent them by an arrow. So the length of the vector will represent its magnitude. So if your problem gives you a 5 Newton force and a 15 Newton force, obviously 15 Newton force will have a longer line compared to the 5 Newton force. So be mindful about this when you're solving problems. If you show a 5 Newton line longer than a 15 Newton line, then that means you're showing incorrect representation of the magnitude. By the way, Newton is the unit of force. We are going to define that in a little while, because we need to know what does N stand for. N is the unit of force, which is called Newton. Then the important part that mass plays in dynamics cannot be ignored. Mass is on which the force is applied. So it is a measure of the amount of stuff that is contained in an object. And mass does not change from place to place. It is the weight that changes. So mass stays same, it's constant, it is a scalar quantity. And it does not change unless you reduce the mass. But as a whole, if you take it to Mars, if you take it to Pluto, if you take it to Sun, and not Sun actually, it will melt there. But if you take it to Mars, since we happen to be launching crazy Perseverance into Mars, so going to Mars is not a difficult thing now, it seems. So we can send this mass to the Mars, and the mass will not change because mass is a scalar quantity. But what will change is its weight, because of the gravitational pull at different places is different. So what triggered the study of forces? We owe a lot to Newton for this, and Newton's laws were discovered or probably formulated by intense mathematical formulas and work that was done by Newton in 17th century. 200 years before the concept of energy and conservation laws were formulated. So Isaac Newton, who was an English physicist, published his work in the Philosophiae Naturalis Principia Mathematica. So it's in one of the museums in London there, and it governed or talked about the fundamental principles that govern forces and their effect on motion of objects. So hence there was the birth of Newton's laws took place. Newton suggested 3 basic laws, purely based on observation, and as we know that our experience suggests that that some objects stay motionless unless you pick it or somebody applies force to it. So Newton was very philosophic, and he observed stuff a lot, and based on his observations he gave certain theories. So this forms his laws form the backbone of the mechanics. So we have already discussed each of the 3 laws under different names, but before you might have observed them, but you don't actually know the formula or actual definition. So the first law of motion was actually first formulated by Galileo Galilei, and it was also called the law of inertia, which suggests that any isolated object that is at rest remains at rest, and any isolated object that is in motion will continue to be in a state of motion unless and until some external force force either stops it from being in motion or sets it into motion. So that force is needed. This is also called law of inertia. Newton's first law is also called law of inertia. And every object continues in the state of rest. If you keep this book on the table, it will continue lying in that state unless and until you kind of move it. So rather than contradicting our experience, Newton's first law of motion states that there must be a cause, which is for there to be any change in velocity. So there must be a net force acting on the object. An object sliding across the table or floor slows down due to the net force of friction acting on the object. So for example, there is force of friction in this direction, there's applied force in this direction. So you will get used to learning about different types of forces: force of friction, force applied, there is gravitational force, there is electric force, and there are many other forces that are discussed. So force of friction comes always into play, whether you're walking, whether you're running, whether you're sliding an object, whether your tires are on the road. Force of friction is always there. Sometimes friction is needed and sometimes friction is not needed. For example, if your tires don't have friction with the road on a circular track, and if it's snowy and icy and you have very less friction, there will be massive skidding and you might be ejected out of the track. So that's why friction roads are salted to increase friction. So in bad weather days, friction is required to avoid accidents. But in some places you really don't need friction, so that can hamper the safe movement. Or if you are on ice skates and you are performing figure dance on the ice skates, it's a very bad diagram. So you don't want friction, you really want to be able to move freely. So friction is good and bad both. So in order to understand Newton's first law, we need to also understand inertial reference frames. An inertial reference frame is one in which Newton's first law is valid. This excludes rotating and accelerating frames. Frame is not a frame that you will put a picture in it. It's inertial frame of reference means if you are in the XY region, where are you in XY coordinate system? Okay, so it basically talks about your location. You can, for example, the room has corners, so the corner represents its location. If somebody asks you to go in the corner, that has a coordinate. So it's basically coordinate system. And before we get into some conceptual part, Newton's first law is completely general and can be applied to anything from an object sliding on the table to a satellite in orbit, to anywhere rather. Experiments have thoroughly verified that any change in velocity must be caused by the external force. Whenever there is change in velocity, there is acceleration involved. The idea of generally applicable or universal laws is important not only here, it is a basic feature of all laws of physics. So very important. We also talked about the property of a body to remain at rest or in motion with constant velocity is called inertia. Newton's first law is also called law of inertia, that I already told you. And inertia of an object is measured by its mass. So higher the mass, the inertia will be more. Mass is a measure of amount of stuff in something. So quantity of or amount of matter in an object is determined by the number of atoms and molecules of various types it contains. So that is one of the differences. Now, when all do you experience inertia? If you have if you are in a car and the seat belt is on, so you know that what happens if the car suddenly stops, the belt protects you from falling out. So that's why there are seat belts and headrests only to avoid sudden jerks. So, for example, the rear end in this case will allow the person to stop safely because he has seatbelt on, he has airbags on, and this is all based on inertia. Supposing you are standing in a train or a bus, and think about the scenario when you are standing and the bus is in motion and it comes suddenly to rest, and you feel that you're coming, you fall forwards. That's because while the bus stops suddenly, you still continue to be in state of motion. So in the same way, when you are standing in the bus and the bus is at rest and suddenly it starts moving, you fall backwards. The reason being that once the bus is starting to move, the bus is in motion, but you're still continuing to be in a state of rest. So these are common examples that are already seen. But what is happening in this example? So you must be seeing this. This is a real example. So a law of inertia is exhibited here. So once it seems that the truck came to halt suddenly, and because of coming to halt suddenly, the truck came to stop, but the big concrete slab continued to be in the state of motion and hence damaged the truck. So really scary situation. Another example, this I already talked to you about, standing in the bus or train, and you can even try this at your place. If you are in person in class, we can try this, but if you are at home with a glass tumbler, you can even fill it with water if you want, and put a slightly thicker page or cardboard and put a penny on it and try to whisk out the playing card or thicker paper out, and you will see that the coin will fall directly down, and that is because while the paper is in motion, the coin continues to stay in a state of rest and hence does not come out, but falls down. So you have to be sure, make sure that you slide it out very quickly. So the net force on an object is always given by the vector sum of all forces acting on the object, and the SI unit of force is called Newton. So we will talk more about when we are talking about free body diagrams. This part will be explained in Newton's second law. Again, these are the forces that are experienced by this block, one in the top direction, one in the bottom direction, and the resultant forces can be found by using the regular resolution of vectors by following the tip to tail method, and we will be able to get the resultant force and the direction. So just as you're used to your lab 2, you found the vectors, the resolution of the vectors and the direction of the resultant vector. So this is some basic definition for inertia. A natural tendency of the object to stay in a state of rest or motion, and mass is a quantitative measurement of inertia measured by kg. Inertial frame is one in which Newton's law of inertia is valid. All accelerating reference frames are non-inertial. Then we come to the most important law of Newton, which is the only one that has mathematical involvement. Newton's second law is the relation between acceleration and force. So this forms the basic dynamics. Acceleration is proportional to force and inversely proportional to mass. So you see this sign F here with a slight with a sigma in front of it. That is called the net force. Or if you're not comfortable writing that symbol, you can also write F net is equal to ma. I actually like to write F net rather than sigma. It's stuck to me. But if you this equation has a lot of applications. If you are given the net force and you are given the mass, you can find acceleration by dividing both sides by m. You can find acceleration A is net force over mass, dividing both sides by m. But you can also use this to find mass by multiplying both sides by m and dividing by a. So 3 different ways you can use the same equation, either to find net force, either to find acceleration, either to find mass. So just as I was saying, mathematically you can call it as sigma F, which is the net force, but you can also write it as F net. Please feel free. Force is a vector, and it's the vector sum of all the forces. Just as I was saying, it can help you find acceleration, which is also a vector, or you can also write it as F net over m. Okay. And now comes the main part, the unit of force. We know now that force is equivalent to mass times acceleration. So the unit of force should depend on the units of mass, which is kg, and the unit of acceleration, which is meters per second square. Kg meter per second square itself in one form was written as Newton N after honoring the scientist who gave us the Newton's law. So Newton is actually a combination of kg meter per second square. So it is the SI unit. This is the SI unit of force. All right. So there's a table that talks about the SI units, and since we know that net force, or you can also write net, is equal to ma, just as I was saying. So the SI unit of mass is kilograms, and the SI unit of force is Newton. The CGS, that is center, gram, and second unit, which is also called that's also called CGS system, has a gram and a dyne in it, and a dyne has a gram centimeter per second square. The British unit for force is given by pounds, and the unit of mass is slug. So there's a comparison for given for the dyne, the pound, and the slug. So before we talk about it, let's see what we learned about Newton's second law. Now, Newton's second law of motion is closely related to Newton's first law of motion. It mathematically states the cause and effect relationship between force and changes in the motion. Newton's second law is more quantitatively expressed than qualitatively, and before we write it down, Newton's second law is a simple equation between force, mass, and acceleration, just as you saw it. We need to know about acceleration. You're already aware what acceleration is. What is the external force? It's an intuitive notion of external is correct. An external force acts from outside the system of the interest. So in mechanics, we are more concerned about the external forces than the internal forces. So supposing you're pushing a wagon, supposing you're pulling a wagon, these are all external forces. So for example, we have an example here, a very simple example of finding acceleration. What acceleration can a person produce when pushing a lawnmower? Now, if you look at the person, he pushes it in this direction. The net force is in this direction because our lawnmower is moving this way, although he's applying the force this way. But he found that the net force exerted, and there must be force of friction also in this way. So direction of the forces is important. So the net force, you can either write sigma in front of it, is equivalent to mass times acceleration. So you have to find the acceleration. So rearrange the terms, and this is a very, very simple problem. You arrange the terms and divide both sides by m, so you get F of net over m equivalent to a. So since we know the terms are given, we have 51 newtons for force, and we have 24 kgs for a mass. we go ahead and divide it, and 51 over 24 gives me the value of 2.1 watt. How will I get meters per second square, the unit for this? We know that Newton is kg meters per second square, and we know in the denominator we have kg unit left. The kg and kg cancels, and we get the acceleration as it's supposed to have the units of meters per second square. So this is a strikingly easy problem, only to show you how to use net force equation, which is also the Newton's second law. So you can always say from Newton's second law. Okay, so next we can work on one more problem. This is the direct problem from your textbook. It's the number 1 problem. What force is needed to accelerate a sled, which is with a mass of 55 kg and acceleration on a horizontal frictionless ice? So there's a person who is actually pushing the sled. So the sled is over here, or probably pulling it. Maybe we should put the sled this way and the person in front, so dragging it. And that force has been given as is to be determined, the net force. But force of friction is 0 because he's saying it's frictionless ice. So the only force that is acting on it is the pulling force. So force is equivalent to mass times acceleration. I'll still say net force, and that's equivalent to 55 kgs multiplied by the acceleration of 1.4 meters per second squared. And once you work on it, you get 77 newtons as the net force. Right? So this is how we solve these simple problems. There is one more problem that we could solve, and I have skipped the in-between problems because they're not directly related to Newton's second law. According to a simplified model of mammalian heart, at each pulse, approximately 20 grams of blood is accelerated from 0.25 meters per second to 0.35 meters per second. You have information about velocities here, and time is also given, and mass is also given. You have to find out the magnitude of force exerted by the heart muscle. Now we are combining kinematics with dynamics. Kinematics is the study of motion of objects, and dynamics is study of forces. So we know that the net force pumped is going to be equivalent to mass of the blood multiplied by the acceleration. But I don't know acceleration, but I do know from kinematics, being a one-dimensional problem, V is equivalent to V naught plus AT. Okay, so if I know time, if I know initial final velocity, I can find the acceleration as V minus V naught over T. And that is what we are going to do here. First determine A by substituting the values. So A is equivalent to 0.35 minus 0.25 whole divided by the time is 0.10 seconds, which comes out to be equivalent to 1.0 meters per second square. At the rate of 1.0 meters per second square acceleration, the net force is going to be equivalent to 20 grams. By the way, you can convert the 20 grams into kilograms. So mass is equivalent to 20 grams, which is, you have to convert it into kilograms. 1 kilogram is 1000 grams. So 20 by 1000, So you can directly put it here, or you can pre-calculate it. It doesn't really matter. There's another shortcut method of writing mass whenever you have conversion from gram to kg. You can simply write this number multiplied by 10 raised power minus 3 kg, because 1 by thousandth is always 10 raised power minus 3. But I leave the decision up to you how you're going to solve, as long as you know how to use the calculator. So mass is 20 grams, which is 20 times 10 to the power of minus 3 kgs, multiplied by acceleration, which is 1.0 meters per second squared. And together, kg meter per second square will form a Newton. So this is basically the value is very, very small, basically, because we are considering the force experienced by the blood. We don't want it a high number. So it's basically given by a small number of 0.02 newtons. Please check the calculations. You should always stop the video when I'm solving the problem. Solve it yourself first and then play the video to know the solution. And lastly, before we wind up the first part of Newton's laws, we'll work on one more problem. When average force to stop a 950 kg car in 8 seconds. So we have to find out that average force if the car traveled 95 kilometers per hour. So what average force is required to stop a 950 kg car in 8 seconds if the car is traveling 95 kilometers per hour? So in order to stop a car, this is a scenario where there's a car which is actually moving. Its initial V naught is 95 kilometers per hour, and then it needs to be stopped. So that means its final velocity V will become 0. Okay, and this whole entire process takes place in a time of 8.0 seconds, and I have to find out how much average force is required. The average force from Newton's law, now we have learned the average force will be equivalent to mass of the car multiplied by the average force experienced during this process. So in stopping it, the average acceleration. So acceleration is V minus V naught. Average acceleration is V minus V naught over T. And we know V naught, we know V, we know T. We can find the average acceleration. But it is better to first convert 95 kilometers per hour into its meters per second, because we want everything to be in SI units. Only then we can write Newton. So we have V naught equivalent to 95 kilometers per hour, and we have to convert it to meters. So 1000 meter over 1 kilometer, and 1 hour is 3600 seconds. So hour and hour is gone, kilometer and kilometer is gone. You have 95 multiplied by 1000 whole divided by 3600 meters per second, which when calculated comes out to be close to 26.39. I'm not going to round it yet, but that we will first find. We are just converting. So now that I have V naught, I can find out acceleration A, which is V minus V naught over T. That is because it's acceleration will be negative because it's stopping. So we have 0 minus 26.39 over time is 8.0 seconds, which gives the acceleration as minus 3.299 meters per second square. I'm keeping all the numbers right now because I have to find the force. Let me see if I have room to use another page. No. So we can go ahead and solve the remaining problem here. To find average force, we'll simply substitute and multiply the two values. And when we multiply mass, which is 950 kgs, multiplied by minus 3.299, we get the average force as minus 3134. But because our least sig fig is 95, so we are going to limit the answer to 3100 newtons. Why 310? Because if this was 3500, if this was 3565, I would limit it to 3500. But since the quantity here is less than 5, so we limit it to 3100. So that's the sig fig answer for the average force. So identifying forces, we'll do some multiple choice over here. To identify forces, you must know what are contact and what are field forces. Contact forces, just as I said, are simple pushing and pulling and rubbing, and this is something that you need contact with. Field forces are at a distance. Interacting objects do not need to be physically touching, just as you know gravity, electric force, and magnetic forces. So based on these concepts, let's try and figure out which one of these are contact forces and which one of these are field forces. So a book lying on top of a magazine on the table. So there's a book which is lying on the table, and there's a magazine on top of it. The force between the magazine and the book is contact force, but the force between the table, the table and the floor will be gravitational. A ball moves along a trajectory through the air like a projectile. So it's only field force because it's under the influence of gravity. Okay. A person sitting on a chair off the floor, on the floor of the room. So I would say there's contact force with the chair, but there is gravitational force with the earth. A magnet floats above another magnet that is lying on the table. So this is a field force. So these are the examples. So basically explaining all the options. Which of the following are characterized as contact force or field force? The force that causes a book sliding across a polished floor to eventually slow down will be a contact force. The force that causes a wine glass to fall downwards after it has been knocked off the table will be our field force, or force at a distance. The force that causes one magnet to repel another is also field force. The force exerted by wind on the sailboat is contact force. The force that causes an object attached to one end of a stretched rubber band to move towards the object attached to the other end is also contact force. So we will, I'll not be naming them, so you can just work on them yourself. So then lastly for today, we'll talk about Newton's third law. Any time a force is exerted on an object, that force is caused by another object. So for example, if you stomp your feet on the ground, you are exerting force on the ground, but the ground is also exerting force in return. So that's why you do not crush your foot all the way in, because there is a balancing force in the opposite direction. So force exerted on hand in this example from the desk, and the force exerted by hand on the desk are given by these directions of the vectors. So we also call it as action-reaction force, or in layman's word, to every action there is equal but opposite reaction, though I don't find it a scientific definition for the Newton's third law. But we can easily define it in terms of contact force, or the force. A key to correct application of third law is the forces are exerted on different objects. So you are not exerting the force on the same object. The wall is exerting force on you, and you are exerting force on the wall in this particular example. So make sure you don't use them as if they were acting on the same object. So there is a passage in the musical Man of that in describing a fight between two people. So they are exerting forces on each other, although the force is not acting on the same object. So that's very important to remember. Whenever one object or body exerts a force on a second body, the first body experiences a force that is equal in magnitude, opposite in direction to the force that it exerts. So you have to remember this definition of the Newton's third law. Other examples of Newton's third law are easy to find. As a professor paces in front of a whiteboard, like now I'm not pacing, but if I'm in person in class, that's when I'll be pacing. She exerts a force backward on the floor. The floor exerts a reaction force forward on the professor that causes her to accelerate forward. So similarly, a car accelerates because the ground pushes forward on the drive wheels in reaction to the drive wheels pushing backward on the ground. So you can see evidence of the wheels pushing backward when tires spin on the gravel road and throw rocks backward. Many times there have been sometimes these gravels can fly off tangentially and strike and hit the glass, and breaking it. There have been many accidents like that, causing a crash. So helpful notation is that there is always one force which probably acts in the forward direction, and the other one, there's equal but opposite action. So there is, we can always say F, for example, in this case, the horizontal force exerted on the ground by the person foot is given by this, and FPG, horizontal force exerted on person's foot by the ground, is given by this symbol. So they are equal in magnitude but opposite in direction, so you have to remember them. And even the rocket propulsion system uses Newton's third law. We can launch rockets based on the gases that are coming out are providing the thrust to the rocket to move forward. So the reaction force is what propels the rocket, and the action is that ignites the gases. So hot gases from combustion will spew out a tail of the rocket at high speeds. So note that you are not actually pushing the rocket. It is the fuels that are that go burn and come out, eject out, giving a push in the forward direction. So for example, we have a feather that falls to the ground. If the force of gravity on the feather is the action, what force is the reaction? Is it the force of the air on the feather? Is it the force the earth exerts on the feather? Or is it the force the feather exerts on the earth? So if this is the reaction, will be the force of gravity on the feather is the action, but the force the feather exerts on the earth is the reaction. Okay, so we will also discuss the differences between mass and weight. Mass is the amount of matter in an object, number of atoms it's made up of. Weight is the gravitational force, and its units are newtons, and it's actually a force, and it varies from place to place. The force on earth For my weight on Earth will be different compared to my weight on Moon or Jupiter or somewhere else, because its weight is nothing but mass times gravity, where g represents the acceleration due to gravity. It resembles the equation Newton suggested, m into a, where a is any translational acceleration and g is the acceleration due to gravity. So both have the same units as Newton in SI system. We can even write f of g for this as the force due to gravity, but some books write it as weight, W, so that we can know that we are talking about weight. And this is the general force in any direction. So you can go ahead and give it a reading. It's the same thing that I have been talking, and the acceleration due to gravity on Moon is 1/6 the acceleration due to gravity on Earth. So it has a value of 1.333 instead of 9.8 that we have on Earth. So force of gravity on the Moon is 1/6 as strong as the force of gravity on Earth. If a 6 kg object is brought to Moon, what will the mass be? Now remember, I'm asking mass, not weight. So just as I said, mass does not change anywhere. So we know it will still be 6 kg. So we will talk about certain vectors and free body diagrams in the next part of this lecture. Okay.